Alright, part 1 has us finding the average force exerted on the ball. So we're going to solve this one using impulse. And impulse is showing us that force times time is equal to mass times a change in velocity. So we know the initial velocity of the ball is going to be 0. It gives us the final velocity of the ball here in the text. So that's our VF. We do know the mass. And the time of impact is down here. That's our T. So to solve for force, we'll just do m delta v, which technically delta v is going to be the final velocity, divided by time. We'll plug in our numbers, and I'm going to get 0.6 times 17 divided by 0.06. Well, that's easy enough to do in my head. So the force is going to be equal to 170 newtons. So that's our answer for part 1, and we're going to need that for later. Now for part 2, it wants us to figure out the time it takes for the ball to get to the plane of the fence. And to do that, it's not too big of a deal. We're trying to find the time for it to move horizontally. So that's going to be the horizontal distance, in other words, delta x. Delta x is given to us down here on the bottom. That, for me, is 20 meters. And that is divided by the horizontal velocity, Vx, V sub x. Now, we know V naught, the original velocity, we know the angle, so we need to figure out the component that's horizontal. That's an easy step as well. So we can just plug in, we know V sub x, that horizontal component, is going to be equal to V naught cosine of theta. And so when we plug in, we're going to get 20 divided by 17 cosine. My angle is 53 degrees. And so my time is going to be equal to 1.955. Now, whenever you're doing your calculations with sine and cosine or any trig function, it's always a good idea to check and make sure that your calculator is in degrees and not radians. Of course, if you're doing this on Desmos, then it should be fairly obvious that it's in degree mode or radians. All right, so for 2 of 4, we got that done. This is our answer for part 2. All right, for part 3, we're trying to figure out the vertical height above the fence that the ball is going to pass. Now, to do that, we need to figure out, well, how high up, at what height is the ball when it reaches the plane of the fence? Now, we already figured out the time, so now we need to figure out the vertical components. So we're going to use the equation for displacement, delta y equals v naught t. Now, in this case, we're talking about vy, so this is the initial vertical velocity, times time. And since this is directional, we want to make sure that we subtract the right-hand side of this. I know the original equation's is positive, plus 1/2 at squared. But we understand gravity's down, the velocity is up. They're in opposite directions, so I want to make sure I get that sign right. So this is the equation we're going to use, and we'll just substitute in. Of course, to get Vy, it's very similar to how we got Vx. It just involves using sine instead of cosine. So this is V naught sine of theta times time minus 1/2 of gt squared. We'll plug in our variables. So delta y is equal to, I got 17 sine of 53 time from before is 1.955 minus 1/2 9.8 9.8 times time squared 1.955 squared. Only the time is squared. Alright, so let me reiterate why we're subtracting. So the first part of this equation, this piece, is giving us the calculation for how high the ball would go up. So if there was no gravity, this tells us how high the ball would go up in the absence of gravity. Now, since there's gravity, we know that gravity is going to slow it down, and so gravity is going to take away some height. That's what the second half, the back half of this is taking away the distance that gravity is going to reduce the height. And so it should make more sense with that explanation why we're subtracting. So if you want to think of it as vectors that are in opposite directions, so we subtract, or to account for the height that's lost because of gravity slowing the ball down. Either way. So my height comes out to 7.815. And some of you would be inclined to box that in right away. That's our answer, and you would get the question wrong. That is the change in height. That's the final height that the ball is going to be at up here above the fence. The question, however, was asking how far above the top of the fence. So there's still one final step here. We need to know the difference in height. So how much bigger is this than the height of the fence? So you still have to actually subtract off the fence height. My fence is 7 meters, and so that's pretty simple to do. So the change in height above the fence is going to be just 0.815. And again, that's because the question's asking how far above the top of the fence, not how far above the ground, how far above the top of the fence. All right, for the last one, what is the vertical component of the velocity when the ball reaches the plane of the fence? So in other words, it wants to know Vy whenever it reaches the time of the plane of the fence. So to do this, we can just use the V naught. Again, we're going to do minus GT. Again, because V naught is up, gravity is down. So I'm just checking to make sure we put the proper sign in there. All right, so for the plane of the fence, we're going to use our time from before. And our initial velocity, this is the y velocity. The initial y velocity, we're solving for the final y velocity at the plane of the fence. So VYF would be equal to V naught sine theta minus gravity times time. Time being the time that we hit the plane of the fence. Plug in 17 sine of 53 minus 9.8 times 1.955. And so my final velocity on the y-axis, VYF, at the plane of the fence, is going to be equal to negative 5.58, and that last digit is 2 meters per second. So in other words, the projectile is on the the back half is on its way down, and so it has a negative y velocity. Okay. So the way the question's worded, it wants the vertical component of the velocity, so it doesn't say magnitude. That means that this answer is going to be negative. You have to put in the negative. All right, there you go.